All right, hey everybody, this is David from the Academic Resource Center, here to talk to you a little bit about Newton's theory of gravity and PHYS40B. So as you can see in this top corner, I have two equations laid out. One of them is Newton's theory of gravity itself, which is g times m times little m over r squared, g being the gravitational constant, m being the mass of one of the bodies, as shown here, little m being the mass of one of the other bodies, and then r being the distance between their centers of mass. Second equation probably looks pretty familiar as well. You might remember v squared over r as being one of the forms of centripetal acceleration, multiplying out by mass here so that it is centripetal force. And the question we want to answer then is relating to this setup here. So if we have an object, let's say it's a planet, let's say it's Earth, of some mass, and then we have a satellite that's going around it, also of some other mass, what is the orbital velocity of the satellite? So this also implies uniform circular motion, otherwise the centripetal acceleration wouldn't be entirely helpful in this case. So it has some v here, denoted by this vector. And as we know with centripetal acceleration, it points toward the center of the circle. And as we know with gravity, everything has to do with the center of mass of the object. Even if Earth wasn't a sphere, if it was some weird shape, the center of mass would be the point where gravity is pulling you toward. So in this case, the force of gravity and centripetal force align into this kind of generic force vector F. So how can we solve for these things? Well, we're going to use the principle of equivalence, and this is a fancy way of saying two things are the same, but if you can put more syllables in it, I suppose it's better. So what is the same here? Well, we know that centripetal acceleration can't just exist because we say it does. Well, it can in these sorts of hypothetical physics problems, but in the real world, that's not the case. There has to be a reason for the centripetal force to exist. In this case, that reason is, as you might have guessed, gravity. So what are the two things that are actually equal here? Well, first of those is going to be, well, these vectors just aren't on top of each other. They're actually the same. That being centripetal force and the force of gravity. So let's state that outright. These are actually the same thing. They're not just on top of one another. All right, and if that's the case, well, we can also say that these equations are the same. So as I move things one at a time, mv squared over r centripetal force is the same thing as gmm over r squared. Okay, and so again, we're solving for v. This v is the tangential velocity. That's the case in centripetal acceleration. That's the case here as well. So we can solve for v in this case. Little m being the mass of the satellite will cancel out since it's on both sides. R, we're going to multiply one r over, so that'll cancel out the exponent here. So crossing things out, and then you'll end up with v squared equals capital G times m, or big M divided by 1r instead of r squared. So where we get is that v should be bigger. E equals, and then the square root in here of gm divided by r. But like I said, this is v squared, so then using the square root, let's see, I'm going to draw a really bad square root symbol. That wasn't too bad. Well, you get the point. So just an algebraic rearrangement from there. It's pretty simple. But of course, just looking at this equation, maybe it might not be clear where it comes from. And so lastly, there's a similar type of operation we can do to find t, which is the period, that being the time it takes to make one revolution around the planet, or whatever objects you have in this case. So the solution is fairly similar to this. It's actually a simple algebraic rearrangement, but in this case, it has nothing to do with centripetal force or acceleration. So I'll leave you to your own devices to see if you can figure that one out. But of course, if you ever have any questions, you can feel free to email us. And that is all for now. So enjoy your quarantine. Please come to us with any questions that you might have, and have a good rest of your day.